Hi, I'm Wilder. What do you want me to say about myself? This is already...
Hello everyone, I'm Triston. Here's our fluids partners, Brian Burke, Wilder Parks, and we're doing a cavitation experiment. And Wilder, can you run us through what the components are here?
So, we have a motor with a propeller on it. And we have a motor controller. It's going to control our speed. And then this is a receiver and a transmitter from an old RC airplane that is going to control it.
Is that a lithium battery?
This is a lithium polymer battery, yep.
Nice, 2.2 volts, and it's just connected to a PVC pipe that we could throw into this tank here and run with this motor.
Yep.
So we're about to see what happens there, and we will increase the speed of the motor until we see cavitation bubbles, and we can calculate it after that.
Alright, you ready?
Yeah. It's hard to see.
What we might want to do actually.
Put it closer. Alright, so we weren't getting the results we wanted with the cavitation experiment. The motor wasn't pulling hard enough to make the bubbles appear or the boiling. So now we're recharging the battery to make sure we have enough power to power the motor, and hopefully we'll get cavitation this time around.
Yeah. Are you ready, kids?
And here we go. Alright, so
I just want to move all this quick so we don't get water all over the electrical thing.
moving stuff so we don't break it. Here we go.
Alright, you ready?
Yep. It's not a little bit over there.
It's a lot of water. Sorry, I'm getting everybody wet.
Oh, it's fine.
Yeah, it's fine.
Here, can you put in the water again so we can see what's happening at the surface? See, the issue happens when all the water is getting pushed over here. Then we get vortexes. And it sucks air bubbles down into the motor, which is unfortunate, because this is not what we want. If we had a bigger tank,
Here's cavitation right there. If you come over towards me a little bit and get it better directly, you can see it. Oh, let's go.
Alright, let's see it.
There you go, 2 seconds. There you go, you see those bubbles? Is it pushing that? It's pushing you.
Alright, like seen in the video in the lab experiment, our results were pretty inconclusive. What we believe happened was when the thrust came from the motor, because our tank was so small, the water could only travel so long before it had to go up. And this upward motion generated a bunch of current in the water, a bunch of ripples, which instead brought in bubbles back down into the motor from the rear end and generated some of those bubble formations we saw. But we don't know if it was cavitation or not, because the two main signs of cavitation was obviously bubble formation on propeller and distinct popping sounds. We did see bubbles on propeller, but we don't know if it was from actual cavitation or from the bubbles being brought from the surface. And we did hear, because our propeller is also really small. We're not going to hear very large popping sounds. We were hearing slight popping sounds, but that could definitely have been from the bubbles being hit by the propeller again. And so pretty inconclusive on that part. So now what I've done here is I drew a cross-sectional piece of our propeller here, which looks like an airplane wing. So what we have here is initial velocity coming in a high pressure zone created by the initial velocity and a low pressure zone caused by the distinct shape of our propeller. Now when this pressure gets low enough, that's when the bubble formation occurs, the water is boiling, and we get cavitation, which Wilder will explain in the next video. But the thing is, with all motors, we have obviously a minimum available RPM and a maximum available RPM. So initially, if we had a very large tank, our cavitation formation would be, somewhere near the max region, ideally. But because we had an increase of velocity into the propeller caused by our small tank in the currents, that increased velocity, we're going to have to drastically increase our RPM. So when we start out with initial cavitation zone of here, our actual cavitation zone would end up here due to the increase of speed coming back into the propeller. So that's a very possible way of error here. So the things we could have done to correct our experiment is, one, obviously use a larger tank, possibly a swimming pool, because like in this situation we had a small tank, the flow path is very limited due to limited space. If we used a very large volume tank, our flow path would go on in a straight line and not be affected by this rebound, this recirculation of water. And we have a constant flow back into the propeller, so we won't have to worry with this increased velocity. Another thing we could have changed is use a larger, more powerful motor. Because if we use a more powerful motor, we could spin this propeller faster, which in turn would help us get a lower pressure with our propeller surface. Because if we get lower pressure on our propeller surface, that'll make it easier to get cavitation. So instead, with the original motor, who could only spin so fast, we can now increase our RPM to where we could hit this ideal cavitation zone. So with a newer motor or more faster motor, we can get a higher max RPM where we can hit that ideal cavitation area.
So we're going to be talking about cavitation, and cavitation is a phenomenon where in a fast-flowing liquid, the pressure drops below the liquid's vapor pressure, and that causes gases to form inside the liquid. And when that happens, the gases can actually, they can burst, or they can't burst, they can collapse in on themselves, creating a large shock wave. And this can be an issue in pumps and propellers and everything like that, where you don't want shock waves hurting your components. So if you think about, so say that we have a propeller, and this is a side view, so this is where it would attach to a boat, and this is the hub, and then there's a blade, and there's a blade, and it's spinning this way. And so if the stream of water is going this way, sorry, this is where it attaches to the boat, so this is a crankshaft right here. I don't want that arrow to confuse anyone. So this is the flow of the water. And what happens is this propeller spins this water speed. As the speed increases, the flow decreases. Now I apologize, I'll move my camera a little bit. As the flow increases, pressure decreases. And the pressure decrease happens right here. So if you imagine a flow line, it's going to come here, come through, and you get here, and nothing is happening here. And so you're actually getting a very low pressure zone right here, which is going to cause some turbulence. But this turbulence in this low pressure zone, if you're going fast enough with your boat, can actually reduce the water pressure below the vapor point of water, and therefore creating these bubbles. And so when these bubbles come in here, they come in, and then I'm going to grab another piece of paper. So if you think about one of these bubbles have to push out with a force, right? And so if you use the ideal gas law, you can figure out the force, the pressure in here, and so pressure equals force over area. And so then you can figure out how the water pressure, and so that corresponding water pressure is pushing back in. And so what happens is, as this cools off and it drops below, as the air inside the bubble condenses, it'll crush together, and it'll crush very suddenly, you know, pretty much from that to nothing in less than a blink of an eye. You have to get this on a high-speed camera really to watch it. And there's a lot of good videos out there of people like exploding things underwater, which is exactly the same principle. And so when that happens, a shock wave can really damage your propellers and like pumps. And so what happens is you get material wear on your pumps, and that's not good, or your propellers, and that's really not good. Some places you can find this are like in water production systems or hydroelectric dams. Hydroelectric dams would be a big one. So let's say we've got our dam here, right? So here's an inlet pipe, and it comes down, and here's our turbine room. There's a turbine in here that's getting spun with water. Comes down and flows out, right? So here's our dam. There's like a lake in here, I guess. Surface of the water. And I guess, I don't know, the dam. I'm not a dam engineer. So it comes down. And so the water in here is going to accelerate very rapidly coming down, both from the pressure exerted here and just from gravity. And it's going to spin this turbine, right? And the turbine's going to generate power, and it's going to add the water back into the ecosystem. But what happens is, with this enormous amount of water, you're going to get a very high speed and some very high pressures, and it's going to create bubbles in here. It can, and this is very bad, because if you create bubbles, suddenly you have this turbine spinning at very high velocity, is now having all of these bubbles that are forming and collapsing very suddenly, and it's going to create wear and tear. So instead of your turbine, you know, a nice new turbine is going to come out, and it's going to look like it's got a bunch of blades on it. This is really poorly drawn, I apologize. So here's your turbine, right? Nice new turbine. And so what happens is, this spins, right? So that's nice. And then as it wears away, you're going to actually get pock marks. And it's actually going to ablate away some of the material on this propeller, or on this impeller, I'm sorry. And so what happens is, as it ablates away, suddenly you get, you know, material inconsistencies, you get blade inconsistencies, and if this is spinning at a super high RPM, what's going to happen is it's going to shatter. And if it shatters at a very high pressure in a very high energy environment, that can do very bad things for a power plant. So there's some examples of cavitation and why it's such a bad thing, and why we have to design around it. Thank you very much.